Okay, well, hello everyone. Welcome to today's webinar, Benefits of Multi-Cycle Analysis. So today we're going to talk about a more topic-specific webinar versus the introductory webinar and some of the other webinars we presented. So the highlight today is a lot of people have asked a lot of questions about our multi-cycle analysis capabilities, and rightfully so. There's a lot of value to simulating multi-cycle, and today I'd like to go through and really describe the capabilities and the benefits for you. Okay, so right now I have all the lines on mute, so at the end we'll go ahead and take questions. So my name is Fred Phillips, and my name is my information is on the screen. So if you have any questions after the webinar, please feel free to email me or contact me. Okay, so what I'm going to do today is I'm going to go through a PowerPoint presentation and really explain the multi-cycle analysis capabilities, and then at the end I'll get into a demonstration as well before we take questions. Okay, so I'm going to go ahead and get started here. Okay, so multi-cycle simulation in SIGMASOFT. So, what is it? Why is it important? When should you use it? How are the results different? And what is required? So that's the agenda for today, and I'm going to go through each one of these. Okay, so first and foremost, why use multi-cycle simulation? So the idea here is to calculate, the heat distribution through the mold, not just through one cycle, but also after multiple cycles. So just like in the real world, in simulation, we want to capture as much as we can as to what's happening in reality. And multi-cycle analysis is probably one of the biggest things that we can do to get closer to reality. So along the lines of, trying to assume the least amount as possible and calculate the most. So calculate more and assume less. So first, it's more accurate. So more accurate mold temperature prediction. So when we actually go through and predict our filling, our packing, our cooling stages, and then get into our stress prediction, shrinkage, warpage predictions, we get a much more accurate capturing of what the mold temperature distribution is. So if we can take into account the mold plates, the inserts, pins, really everything that consists of that mold in the simulation. And then with that, gain an understanding then of where the hot locations are, where the colder locations are, and give you some guidance for actually designing your cooling system. So if you know where the hot spots are, then you have an idea where to put your cooling lines, or where to put a baffle or a bubbler, or even some sort of thermal conductive material. And then, if you look at, different mold materials, so look at the impact over time. So if you have say a beryllium core insert that's touching a P20 plate, after one cycle, you're going to get a certain amount of heat conductivity that's going to occur between those two materials. But after 5 cycles, it's going to be even more. And then after 10 cycles and so forth. So the more cycles we run, and the more those materials are subjected to heat load from the polymer the hot polymer injected into the cavity, but also our cooling system, right? How that cooling system is extracting heat away from the cavity, which is our goal. Or if we're putting in heater cartridges, so the opposite effect, heating up that mold and trying to heat up the cavity. So if we're simulating some sort of a thermoset, maybe an epoxy, for example, we want to use that as a catalyst for our curing. So also the ability to see that impact, not over just one cycle, but over many cycles. And then if we look at our hot runner system, right, so putting a great amount of heat load, if you have a hot runner manifold and hot runner drops within your mold, so let's look at how that is affecting your mold temperature as well, but also the part quality cycle after cycle. So as that polymer is sitting in that runner system, you have a residence time. So how long is that polymer sitting in there, and how is that heat load after 1, 2, 3, 4, 5 cycles, again impacting the heat distribution, the heat flow through that mold. And then at the end, optimizing things like cycle time, reducing setup time, minimizing that startup and production scrap. So being able to simulate what's going to happen before you actually put the mold in the machine. So how many cycles does it take for that mold to reach a steady state condition? So when you actually go in and put that mold in, we don't want to sit and make 30, 40, 50 pieces of scrap because the mold hasn't reached a certain equilibrium yet. So knowing that going in, again, gives us much more valuable idea to minimize that setup time, but also minimize not only startup scrap, but also production scrap. Okay, so what's our goal it's always make good parts, right? So everybody on this call, everybody watching this webinar, that's what we're in the business to do, is make good parts. And not only make good parts, but make them quickly and consistently. So if we can do this sooner in the process by doing a lot of things in a virtual world, by simulating many cycles virtually, and then once we actually build that tool and make those decisions from the analysis and then put the tool in the machine, we can get there a lot quicker and a lot more consistently and with a known and repeatable process. And again, we're all in the business to make good parts, because at the end of the day, we want to be profitable. We want to make money for our companies. And all this can be achieved one step further by using SIGMASOFT, and SIGMASOFT's multi-cycle simulation is a very valuable key to that. Okay, so first shot success. So what is first shot success, right? Just what it says. So when that part comes out of the mold during the first sample, we want it to basically meet our needs, and meet those quality needs. And with SIGMASOFT, this is achievable. And I've talked to a few of our customers who are using SIGMASOFT for just this. They're simulating everything that they can in a virtual world, and by being able to bring in all the mold components, by being able to run multi-cycle analysis, by really capturing as much of reality as they can in the simulation, they're getting a much more accurate idea of what's going to happen. And if you have a much more accurate idea, then you're going to make better decisions. And that's really the goal with simulations, is to make the best decisions up front before we ever cut steel, or before we ever put that tool in the machine and start making parts. We want to know as much about the process as we can. Okay, so accuracy. So this really will be the theme, and I think this is the theme for all of simulation. Why would you use simulation if it wasn't accurate? And I think that truly, over the years, a lot of companies have seen some value at a simulation, no matter what package it is. But you only get to a certain level of accuracy, and a lot of this comes from what's being calculated. There's a lot of assumptions, and some packages assume a lot more than other packages. And with SIGMASOFT, we don't assume that much. We actually give you the ability to bring in the entire mold base, all the mold components, simulate the entire production cycle, what's happening before the mold closes, after the mold closes, when the part's ejected, even when the part is sitting on that conveyor belt for 30 minutes, 1 hour, 2 hours. What's continuing to happen as that part continues to cool and stresses continue to relax, and the part continues to displace or warp. So if we look at multi-cycle simulation, we can look at really this in two areas. So it provides more accurate filling results. Now, filling pattern probably isn't going to change that much depending on the multi-cycle, from say, if you run 5 cycles versus 10 cycles. But, I have seen cases where you could have trouble filling a cavity because you think that the mold temperature, or the simulation is saying that the mold temperature is lower, so you're actually predicting a short shot situation. So if you run just 1 cycle and you have a cold mold, then yeah, it might predict that you're going to have a short shot. But if you were to run that mold through, say, 20 cycles, and then you go say, wow, the temperature difference is drastically different after I subject the cavity to 20 cycles of heat, 20 cycles of hot polymer being injected in there, all of a sudden a warmer mold temperature might allow you to fill that part. So you might have an inaccurate prediction, or the simulation is saying you have a short shot, but in reality you don't. So again, multi-cycle simulation gives you that better accuracy. And then more importantly, really where you see the benefit is in the packing and cooling phases, and then the resulting stress, shrinkage, and warpage predictions that occur. So your mold temperature is very important. And this is one of the strongest things within SIGMASOFT that we can't talk about enough. Is it's one thing to simulate your part geometry. There's a lot of value there. But if you're just assigning a generic piece of steel around it and assigning it a condition, saying, hey, it's a P20 mold and it's this temperature and 1 cycle and these are my results, and that's not really reality. Nobody's doing that in the real world. So when what happens in the real world is mold temperature is one of the most important things that happens. This drives your solidification rate. How fast the part cools, how fast a semi-crystal material crystallizes. And of course, that solidification rate is going to influence your stress in the part and your distortion of the part. And it's also going to influence your packing rate. And as we know, packing influences distortion as well and overall part quality. So it's not just a matter of saying, hey, I'm going to do a couple cycles of simulation. Being able to simulate something close to reality has a huge impact on all of these things, on your packing, influence your stress, your distortion, your cooling, and so forth. Okay, So if we look at geometry and process optimization, so a lot of people use simulation for one obvious need is your cooling design, right? When you first get a part, then you start designing in the components and the different plates and the different core inserts. At some point you're going to be sitting in that meeting room deciding, where do I put the cooling channels? Where's the best place to cool this part? Where are the hot spots going to be? And without simulation, you really don't have that idea. You actually, you would have to build a prototype mold to even get to that decision-making process to know where the heat buildup is. So again, with SIGMASOFT, we give you that ability to really look at the entire temperature through the mold and really understand, where the hot spots are, where the cold spots are, and then where to put that proper cooling. And also, since you have the ability to bring in ejector pins, also, what's the ejector? You always have to make that sacrifice between, can I put a cooling channel here, but I need an ejector pin here. So we also have ejection analysis. So as a sidebar, you can also simulate your ejection design and simulate, okay, do I need a pin here? Or how many pins do I need to eject this part? Then concurrently, you can design your cooling system and your ejection system within SIGMASOFT and simulate both of those and come up with a happy medium of the best scenario. And of course, in a lot of situations, of course, the process and the geometry are married, right? So, in the real world, that's what happens. Your geometry is locked in, and you have a certain process window around making that design or making that good quality part. So being able to simultaneously optimize our geometry and our process within simulation, again, one more step closer to reality. We want to consider the process when we're designing our geometry or optimizing our geometry, and we want to consider our geometry when we're optimizing our process. And of course, everybody wants a large process window, right? Because you're making fewer bad parts. So, multi-cycle simulation takes all these together so we can visualize and understand all the interactions before we build the mold. Okay, so by multi-cycle analysis, what do we mean here? So in a simulation world, just what you would think, right? So we're going to just simulate multiple consecutive production cycles. So on the screen here is just a snapshot of the SIGMASOFT setup interface where, in this case, we have our material definitions where we assign our polymer and our mold, whatever tempering we have. So we refer to tempering as a cooling system or a heating system, such as the heater cartridge or cooling channel, baffles, bubblers, and so forth. Heat transfer definitions, so understanding the heat transfer that occurs within every mold component that's in contact with another. And then here we have multiple cycles that are set up. And really what's happening here is that we have, say at the end of cycle 2, the temperature and the mold temperature at the end of cycle 2, the mold temperature at the end of cycle 2 is your input for cycle 3. At the end of cycle 3 is your input for cycle 4 and so forth. Then we start to understand what happens over the multiple cycles and try to find that part when our mold temperature reaches a cyclic equilibrium. And we can look at that a few different ways. So one thing here is we have what's called a heat balance summary. So in this case, we've run, looks like 25 cycles. And usually we'll run a few more cycles than we need as a first pass. And this can be very fast. I mean, you can run 20, 40, 60 cycles really in a couple hours. And there's some techniques there that we teach through our training classes that allow you to do that very efficiently. So in this case, we've run 25 cycles, and we go here and look at this, and you can see that, really around the 10th cycle, 10, 11, 12, that's when we start to reach that equilibrium or that steady state condition where we know, okay, our mold temperature, our heat balance on our mold has started to level off, and that's kind of where we want to be. So for further simulations of this design and different scenarios that we're going to analyze, we want to run about 10, 11 cycles, and then we're going to get a much better accurate picture of filling, packing, cooling, stress, warpage, and so forth. Okay, so I'm going to go through here a couple of examples and really show you, why multi-cycle really is important. Because really the results are different. And again, if you look at simulation, what do most people want? The first thing you want is accuracy. And then you can also compound that onto something that's very comprehensive, but also easy to use. So SIGMASOFT gives you all of those things. Okay, so if we look at cycle 1, you can see here, so what we've done here is all I have is I've turned on a few of my components. So I have my A side, my B side. And you can see the temperature throughout the cavity. So this is just after one cycle. So you can see the temperature distribution there. And I've used the same scale to be consistent. Now after 15 cycles, look at the difference in temperature inside that cavity and of the mold itself. So we have 15 cycles of running that cooling through there, or in some cases a heating, a hotter material than would be considered heating the mold. And this snapshot is actually taken 10 seconds into the packing phase. So I can, of course, do this at any time during my cycle. Just for this example, I picked 10 seconds. I could have done this at 5 seconds or 1 second or 20 seconds, and you'd still see the same type of difference. Cycle 1 is going to be drastically different from cycle 15. And again, the idea here is that we want to use cycle 15 because this is a lot closer to reality than, say, cycle 1. So same mold, now I've just stripped away, and now we're just actually looking at the B side and just look at the open cavity. And again, you can see the temperature difference here. Same scale. You can see we have a much greater heat load around that core after 15 cycles. And again, that's going to affect a lot of things. That's going to impact your flow front. That's going to impact your solidification rate. That's going to impact your gate temperature, which is going to impact your gate freeze. So again, I can't imagine a world when you would not want to simulate multiple cycles, because in the real world, you're running many cycles. And then here we just have the A side, so I've just flipped it around and showed the same thing. So same idea, right? Between cycle 1 and cycle 15, pretty drastic difference in temperature between the two. Okay, so here I'm actually going to animate that. So I'm just going to go ahead and animate this. And at the bottom here, if you want to watch, here it says cycle 1. So again, 10 seconds into my packing. And I'll go ahead and just animate this, and it'll go through the full 15 cycles. And you can see that after about the 12th, 13th cycle, you don't see such a big temperature difference. You really see that drastic difference, when it goes, through 1, 2, 3, 4, 5, 6, in those first, say, 10 cycles, you see a pretty drastic difference. And that's when you start to see that leveling off in the simulation. And again, here's the same mold, same example. I've just put the mold plates back together and animated again just to show you a different view. Again, 10 seconds into packing. Okay, so why is this important? So it's one thing to look at the mold temperature, right? So there's a pretty big difference there, but there's also the actual part quality itself. So if we look at cycle 1 here and just say look at this part, so what we have is deflection. So if we look at our z-axis here, so the part is actually deflecting inward or downward here in this orange area, and then upward here in the blue area. So we have a negative z in the blue and a positive z in the orangish red. So if we look at cycle 15, we actually have a 26% increase in displacement here, and 17% increase in displacement here. And of course, if you take those two combined, the overall distance from cycle 1 to cycle 2, we're looking at a 20% greater warpage prediction after 15 cycles as we were after 1 cycle. So again, very important, especially for high tolerance parts, to look at the impact on really the final part quality. And again, with SIGMASOFT, calculate more and assume less. If we have this geometry, why not simulate it? Okay, so a lot of people would ask, okay, well, what do we need to do this? So first and foremost, we need our part and runner. So probably the two things that everybody that's done analysis before has asked, or that is asked for, my part and my runner, and even my cooling design. So you can do the cooling design. You can bring in a pre-designed cooling system from CAD or create it in CAD. Or you can go ahead and create it inside of SIGMASOFT. And even if you bring in your mold plates that have the drilled holes, we have a lot of great CAD tools within SIGMASOFT to actually boolean out those cooling lines. So we can get that physical cooling line geometry very easily using SIGMASOFT. And then the tool. So this is one thing that most people aren't used to getting, and it's a very methodical approach. So early on in the process, you may only have your part design. So that's what you'll simulate first. Okay, where do I put my gate? Where do my weld lines appear? So do more of your part design optimization. And then once you actually start designing the tool, then you start bringing in plates and bringing in your inserts and start looking at cooling lines and anything that may impact that. So even ejector pins or ejectors that are touching the cavity, there's heat transfer that's going on there. So why not consider that? In some cases with some materials and in some high tolerance parts, that can be the difference between a good part and a bad part. And at least start with, so if you don't have all this geometry, at least start with a cavity block size that's realistic. So even in the simulation, if I don't have all this geometry, at least what I can do is at least take and just create a block of steel or a block of H13 or S7 or P20 or beryllium copper, some sort of material that's we have a large database of materials, at least put that around the cavity and simulate that. So we know how far it is from that cavity through that steel to the outside, which is your ambient air condition. But again, keep in mind, every time in simulation we make an assumption, we introduce a chance for error and inaccuracy. And again, I can't say enough that simulation has been around for many, many years. But if you ask a lot of people, they will mostly all say that yes, but it has limitations. And usually the limitations are they believe it's only accurate to a certain point, and they can only trust it to a certain point. And the reason for that is that you're making a lot of assumptions, and especially on your imports. Your two biggest things bringing in are your geometry. So we want to capture as much of our geometry as we can, and also your material properties. So we want to make sure that we have, exact characterization of that material, and not just generic material. So I know there's other simulation packages out there that have large databases of material, but a lot of that material is generic data, supplemental data, single-point mechanical data, and that's why you don't see the accuracy in simulation that you desire. SIGMASOFT gives you that. Okay, so here's another example. So if we look at, in this case, we actually have our cavity and core inserts turned on. And I have it scaled here so I can really highlight the temperature distribution through the inserts. So the red is actually our part, our runner, and really our polymer. And here you can see after one cycle of just filling, you can see here that the temperature of the mold and even our cooling here hasn't had a huge impact just after that one cycle. But if we go here after 21 cycles, you can see a much greater impact. Now the cooling is really starting to pull that heat out of the tool, and it's actually starting to cool that steel of that core. But also around the perimeter here, you can actually see the heat load that's actually growing. So we got 134 versus 125.9. So what is that? 8-9 degree temperature difference just of that insert over those cycles of injected polymer and cooling. Okay, so another thing we need is our process. So just like in the real world, so setting up a molding machine, so in the simulation we're going to set it up just as we would. So again, first thing is to specify all of our materials. So our polymers, our different mold steels, our cooling materials, or heater cartridge or heaters, things like that. And then here, if we look at our mold itself, now in this example, and the example that I'm going to show here in the next few slides, is I have a geometry where I have a few components that comprise of my movable half or my B side, and then some components on my fixed side or my A side. And then I have my A plate, my top plate, my B plate, I have ejector plate, core block, I have several different components here. So being able to bring those all in and specify what each of those materials are. Maybe your plates are P20, but maybe your insert is H13 or S7 or M2 or something like that. And then setting up your entire process. So here we have anything that comprises of our preparation phase, so any placement of inserts, even before that, service time, then how long does it take to close the mold, then any type of delay time, set up our full filling packing profile. So our fill time, you can specify by time, specify by flow rate, and then what point do we switch from velocity control to pressure control, and then define our entire packing profile. We're going to pack for this period of time at either this pressure or this percent of the transfer pressure, and then how long are we going to cool it or cure the part, and then when do we open the mold. And you can see here that we actually have our mold open time specified at 40 seconds for the movable half, 37 seconds for the fixed half. And the idea here is that when that mold opens, the part is actually still in contact with the movable half for an additional 3 seconds. So again, it's very important. And again, it goes back to what I keep saying, not to sound like a broken record, but calculate more and assume less. If that hot part is in contact with the B side or the ejection side for an additional 3 seconds, it's touching that hot steel or that cold steel for an additional 3 seconds. That's going to impact your warpage. And then going through and specifying all the different parameters here, your cooling and so forth. And you can see, of course, here I have my multiple cycles specified. Okay, so what we can also do, so similar to what I showed before in my heat balance summary, so what I like to do, and a lot of our software users like to do is the ability to put in virtual thermocouples. So I can actually put a virtual thermocouple anywhere in my whole design. So what I like to do is put a few in the steel, maybe an inch or so above my part, and then maybe up in a core, or maybe between my two cavities. Say if I have a 4-cavity tool, maybe put them in between, and really look at that heat load over time. And again, gets you that idea when you reach that equilibrium or that steady state condition when your mold temperature doesn't change drastically from cycle to cycle. So in this case, I'm looking at a thermocouple where you can see we have definitely temperature increase here, and then around just under shy, maybe around 1,000 seconds after multiple cycles, and we actually start to see that leveling off, and then it's pretty consistent for the rest of the run. And how valuable is this, right? To really understand when that mold reaches steady state before you actually ever put it into the machine. Okay, so here's another example that I'm going to go through. And in this one, actually, I've highlighted some of the temperatures. So what I've done here is I've taken a 4-cavity tool. So what we can see here is we have our B side, and I have a core block on my core pin. You can see my runner that's cut out here. And I've taken a snapshot of temperature 1 second into the packing phase. So I have the same scale on the right side for these next few slides. And then, so I have the temperature at the top of my core pin. I have the temperature at my gate. I have a temperature at the side of my core pin. And I have a temperature just at the top of that core block. So if I look at this at 184, 169, so here after 15 cycles, that core pin is increased by 77 degrees. You can even see the temperature outline. And again, it's the same scale here, so really you're looking at, now it's, a lot redder than it was compared to that previous slide. Our core block temperature is increased by 40 degrees. And even my gate is increased by 11 degrees. So if we look at that, that actually has impacted my gate freeze time. So just by that temperature increasing, I've actually, my gate freeze time after running my 15 cycles is actually 4 seconds. After 1 cycle, it was only 3 seconds. And also, if we highlight area here, I know it's probably a little difficult to see a huge difference here, but what I'm looking at here is areas of the part that are still molten versus which are solidified. So I've taken a snapshot at gate freeze. So all the areas in red and blue are still molten. The areas, and the only difference is the areas in red are still having the packing pressure being applied to them. So there's still pressure on that system. The areas in blue are molten, but they're free to shrink. And I've circled 2 areas here. So look at this area here. We have, this is our molten area that's free to shrink. And over here, we have a little bigger area. So again, we have probably a stronger chance for some sink marks or some displacement or voids in this area that, now that we're simulating a more realistic situation after 15 cycles versus after 1 cycle. And again, as I pointed out before, say, how does this impact things like warpage? So in this case, I'm going to look at my distance across the part in the direction of flow. So if we look in the X direction, I can see that this is 87 thousandths warping inward. This is 78 thousandths warping inward this way. So after 15 cycles, I actually have 27% more warpage than I did from cycle 1. So again, and if this part has to be assembled or mated onto another piece, which in case this one does, that could be a very important prediction. And depending on the material, you might have a much more drastic warpage difference. In this case, I'm actually simulating a glass-filled PBT. So not a huge amount of warpage, but enough that it's significant. We want to simulate the true mold conditions, 15 cycles versus, say, 1 cycle. Okay, so in this design, what I've also done, so I said, okay, so the previous design, everything was P20. My core blocks, my core pins, my plates, everything. So what I did here is I kept my mold plate at P20, but I changed my core blocks and my core pin to mold max cores to see if I could get a better, basically better heat, thermal conductivity or heat transfer going through the mold and extract that heat out better. So with the mold max cores, 1 cycle did not show a significant change from the P20. So, and again, just running 1 cycle, yeah, I noticed a difference. My core pin temperature changed 1 degree. My core block temperature reduced 4 degrees. But if I were an engineer running this part and had to make that decision and say, do I make everything P20? Is that good enough? Or do I make my cores mold max? I would look at this result with just 1 cycle and say, you know what, not a huge difference. I might as well just stick with the P20 cores. But if I look at the cycle, and so sorry about it, it says cycle 20, but it's actually cycle 15, the core pin temperature actually increased by 45 degrees, and the core block temperature increased by 30 degrees, compared to the mold max after one cycle. If you look at that as a whole now, so again, so if I look at just the one cycle situation over here, not a huge difference, 184, 183, 170, 171, 169, 164. But if I go over here after 15 cycles, and I'm going from 261 down to 228, 211 down to 194, 265 down to 229. Now I'm going to look at this and say, you know what, maybe I should use the mold max, because again, it's a much more realistic prediction of what's going to happen in reality. After 15 cycles, yeah, that higher conductive core is going to have an impact. So we go ahead and animate just this temperature as well and show you how the mold heats up over 15 cycles. And this is 1 second into packing. You can see that most of the change occurs within the first 8, 9, 10 cycles. And then after that, we don't see such a drastic change. Okay, so with this, I want to switch gears, and I want to actually get into the software for a few minutes and just show you some of this. So it's one thing to show you some slides, but I think it's always nice to get into the simulation. So let me go ahead here. And so first of all, so what I have here is I have a design. So this is a mold that I've brought into the analysis. And it's a little simplified. I've taken out some of the holes and some of the bolts that I've left in, some of the cooling inputs and the plates and insulator plates and so forth. So what I want to do here, I'm actually going to run a animation here just to show you really what's happening with this tool, and then we'll get into the results. So do this pretty slow, that way you can really see it through the internet. Okay, so now we have our mold opening, and a multi-direction mold open there. So now we switch to transparent. You can actually see the cooling channels that run through the tool. You can see our hot runner manifold over there on the right with our drops. And the parts are in blue. So we're making blue parts today. Or I guess at this point they're cold, right? So they can be ejected. I pushed off the core. Now our mold's closing. Then we'll inject our next shot. Okay, so with that, now I'm going to actually get in and look at the results of this, or just show you a couple things in the software. So within this, I have my different entities or layers or components, whatever you may want to call them. Now I should point out here that some of these are actually in German. So I actually got this project from one of my German counterparts just recently, and this is really the first time I've gone through and done this. So my German to English isn't excellent, so I haven't really translated these, but I think you get the idea here. So what I have is my parts are turned on. I should turn those off over the core. So now I just see my core, and I just have my movable half turned on. So I'm going to leave it at that for right now. Go to my results. So I have different filling results, cooling results, stress, so forth. So under cooling, if I go to temperature, I can see here I have my multiple cycles. So if I just go to cycle 1, let me just say, let's just be consistent. So this will be 10 seconds into our packing phase. Just look at that temperature. And so in this case, I'm going to go ahead and change my scale as well to English units. How's that? All right. So you can see here we have our core. Obviously, fairly hot after one cycle. So let's go down here after 5 cycles. pick the same. So again, that was 10 seconds into packing after just one cycle. So now let's go 10 seconds after 5 cycles. So you see a pretty big difference there. You know, our mold has changed the temperature there. I can even query on different areas of the part here, even between the out here. Let me just go back here and show you that again so you can see the temperatures change. So 222, 194, so yeah, 217. So the mold out here hasn't changed too much because we're pretty far away from the cavity still. But inside here you can see a pretty big difference in heat load. Now if we even go to the 10th cycle, so again, pretty big difference there, and there's multiple points of value here. You know, so one is to look at the mold like this and learn how to design and figure out how to design your cooling system the best way possible to pull that heat out. And then of course the other side of it is you know, making sure that we have the right conditions so we predict our filling, our packing, our solidification phases properly, and really get a much more accurate understanding of what the shrinkage and warpage or stresses in the part may be. So if I take this also and let me go ahead and slice this. So if I'm going to go ahead and go in the Z direction. So I'm going to slice right down through this mold. So you can see we have our cooling channels there that run through. So here's where we have a baffle that actually goes up into that core. So if I actually switch my cutting plane to the Y direction, I can actually go through and see that as well. So here we can rotate that. So you can see my cooling then comes up through that core, so forth. And I can even turn on that cooling line. See so now I've actually turned on the cooling, so we can actually see what the temperature of the coolant is as well. Not only the cavity of the coolant, but the channel of the coolant, but also the coolant itself. Turn that back off. And I can also go ahead and turn on my parts. See what they look like on top of the cores. All right, so we can see there. Now I haven't adjusted my scale here. Now I could definitely do that and go through and scale that, make it user friendly. Change this to something like 200 and apply that, and that way you get a little better representation of, at least keep it consistent with and without. Probably didn't need the best scale there, but I think you get the idea. And we can even go back here and just turn on our entire mold. All right, so go ahead there. So now we can actually see the heat load there through the tool. Again, we can look at these results at any point in time. We can go to our 16th cycle, go 5 seconds into the packing phase. So forth. Turn off our slicing. Go ahead and slice down through the Z direction, through our hot runner manifold, down into our cores again like we did before. All right, so that's really what I wanted to show today. I just wanted to highlight, again, the differences in multi-cycle, but also some of the capabilities of simulating the entire mold and the value of being able to bring in all of these components into the analysis. All right, so here I'm just going to go ahead and do a summary slide, and then we'll open it up for questions. All right, so again, first shot success, consistently, that's a goal. How close can we get when we put that tool in, to having that first shot success? Making good parts, within the first shot or within the first couple shots, and we can even simulate when that mold reaches steady state. So even if you wanted to simulate the fact where you go ahead and close the mold, turn on the cooling, and then go have a cup of coffee, and then 40 minutes later come back, you can simulate that and see, okay, what would the mold temperature be after that 40 minutes, while the mold's closed and that cooling is running through there, or at what point does the mold reach production temperature. And obviously, a very repeatable process by being able to simulate all this up front, and all the things that we've talked about, right? Optimize your cycle time, reduce your scrap, improve part quality, all the rework, the lack of downtime because you don't have that rework, and lack of labor costs, again, that's required to pull that mold out, go make a change a cooling system, open up a gate, and so forth. So again, calculate more and assume less. And it's always verify the final design with multi-cycle simulation. So a lot of our customers, again, they'll start out maybe just a part itself. Start early on when they have the information. Then as you gain information through the process, keep bringing more and more of that into the simulation, and do your final verification. Make that part of your process. Doing multi-cycle simulation with your components, and really understand what's going to happen. So when you build that tool and put it in production, you're much more prepared. And if you look at it competitively, how many of your competitors are doing this? How many of them are starting out with this head up, this leg up of saying, hey, we put the mold in, we're not making scrap. We're only making 2% scrap. Your competition might be making 10% scrap. You might have a 37-second cycle time. Somebody else making a similar part might have a 40-second cycle time. So those little changes can save you hundreds of thousands of dollars just by doing this up front in the simulation. And create a simulated design process. I think I meant a GO, not a GA there, but garbage in, garbage out, right? So the more you have coming in, the better accuracy you're going to have on the back end. Okay, so with that, we'll go ahead and open up to questions. So my information is on the screen, and just want to, again, if you have questions that you'd prefer to ask me outside of the webinar, please feel free to call me and or email me. I'd be more than willing to answer your questions and show you, really why SIGMASOFT, why we label it as the next generation of simulation software. This is something that people have not used, have not seen, and it's taken simulation to an unprecedented level of accuracy and ease of use. So, all right, let me go ahead and go over to my question panel.